Welcome to Study Loop.
All right, hello. So today we'll be talking about finding the Lewis structures for these two compounds with the lowest formal charge. And the easiest way to do it is to just draw out the Lewis structure as we've learned with the method of finding the central atom, drawing the peripheral atoms, finding valence electrons, drawing the single bonds and lone pairs, and then calculating formal charge and seeing where we're at. Ideally, our lowest formal charge is 0 for all atoms. And this shows that we have the most kind of ideal or most stable compound. And that's what we're trying to aim for. So let's start by drawing the Lewis structure. So we have our iodine in the middle because it's lower in period than our fluorines, and because they're in the same group. So you take the one that's lower in period. And also it's only one. And because fluorines can only form one bond, and there's 5 of them, more likely they're going to be in the periphery here. So those are your 5 fluorines, your 1 iodine, and then you can draw your single bonds, and then you'll fill in the rest with the lone pair electrons. But first, let's calculate the number of valence electrons to see how many of those we need to do. We see we have 7 for the iodine plus 7 for each of the 5 of the fluorines, so that gives us a total of 42. We've taken care of 10 here with the single bonds. We need to then cover the remaining 32 with lone pairs. So let's just draw and complete the outer octets, outer valence shells for the fluorines and give them a full octet. That was a little bit off, sorry. Redraw that one. There we go. Okay, and then now you can see that we have 40 electrons because you can just take the single bond to represent 2 plus the 6 lone pair electrons, so that's 8 times 5, 40. So we're missing 2, and those 2 are going to go as a lone pair on the iodine here. So now we're all set for drawing our Lewis structure. Let's go ahead and calculate the formal charge. The formula to calculate formal charge is the number of valence electrons, and not to get confused, but it's the number of valence electrons that, just when you think of fluorine, it should have based on the periodic table. Then now we're looking at what is actually being happening. So we subtract the number of unshared electrons as the molecule is bonded, plus, so that's within these parentheses, plus 1/2 of the number of shared electrons. And yeah, don't get confused. There's actually not a lot of overt. You don't necessarily have to fully memorize this exact equation. Just try to intuit it and try to make sense of it in terms of how what the formal charge takes into account is the number of valence electrons minus the number of lone pair electrons. That's the unshared electrons. And this 1/2 component, 1/2 of the shared electrons, is just what you're doing is you are splitting the single bonds. So you're basically displaying the sharing of electrons between the I and the F here, and therefore you take half of that. So basically a trick is when you have all single bonds, the half of the number of shared electrons is just the number of single bonds, because single bonds represent 2, half of the shared just represents 1 electron here, so you can just calculate the number of single bonds and that'll give you this half component. So for fluorine, we have 7 valence electrons. We subtract the 6 lone pair electrons, the unshared, plus half of the bond, so that is the 1 out of the 2, and that gives us a formal charge of 0. So that's good for fluorine. Let's do it for iodine. So for iodine, we have also 7 valence electrons minus just the 2 unshared here, and as I said, the half of the shared, so sorry, 2 of the unshared plus the half of the shared electrons is just half of the electrons that are shared in these single bonds. So that's just the number of single bonds, just splitting those in 2 as so. And that gives us 5 that are half of the shared. So that's 2 plus 5, 7. 7 minus 7 gives us 0 for iodine as well. So we now have formal charges of 0 for both iodine and fluorine, which tells us that we have our Lewis structure with the lowest formal charges here. Next, let's do it for aluminum anhydride. So aluminum in the middle. We have 4 hydrogens here, and aluminum goes in the middle because it's the only atom in this compound that can form multiple bonds. We draw our single bonds. We also have a negative charge here as indicated in the problem, and we are left with making sure that we have the right number here. So aluminum has 3 valence electrons, given that it's located below boron in group 13, which tells us that we have 3 valence electrons based on the p orbitals. And then we have 4 times 1 because there's 1 electron in every hydrogen. 3 plus 4 from the negative charge gives us 8 total valence electrons. And based on the fact that we have 4 single bonds, we do have those 8 electrons, so we're all set. Remember that the negative charge tells us how we got here, not the current state. To find the current state and number of electrons, just look at the actual compound itself. Now we can go ahead and calculate formal charge based on the formula above. Let's take aluminum. So we have 3 valence electrons minus there are no unshared electrons, and then half of the shared is just the number of single bonds, 4 single bonds. So that gives us a -1. So this is an ideal, but given that hydrogens can only form one bond, this is the only way to kind of set up this molecule really based on the molecular formula. So the -1 is kind of just has to happen given that we are kind of overloading the number of valence electrons that we have normally have on aluminum. So we normally have 3, but we need to have 4 in order to form 4 bonds. To calculate the formal charge of each of the hydrogens, we have 1 valence electron. Once again, no lone pairs on any hydrogens here, so that's no unshared, plus half, so each hydrogen is forming 1 bond, right? So it's half of the shared, so that's 2 shared here, so that's just 1. And that gives us a formal charge of 0. So all 4 hydrogens have a formal charge of 0, which is low, and this -1 of just this one atom, as I talked about, is unavoidable. So this setup represents the lowest formal charge